I got a spam call from Washington to cut me off. I'm back. All right. So yeah, you would multiply this by, like if I have 3 particles of gas, 3, then I would multiply this by 3. Okay, this is for 1 particle of gas. Okay, so I wanted to go over this equation, problem number 1 on last year's quiz, why it was there, how you would solve it, and now you have the answer key, so you can go back and go, oh, okay, well, okay, now I kind of see what he's talking about. Okay, that's what I'm talking about. Probably won't see it, but you might, so if you have it on here, we need to go over it. And that's where it comes from. That is the energy of 1 particle of a gas. Okay, moving on. Moving. The next part, now we're below the line, people. We're below the line. Here's our handout and notes. Actually, let's go to the last page. And I've got some addendums on here that I added on. One of them is on the equation for conductivity. So we went through that with you. And we had a problem on last year's quiz about that. You should know it. Then here, I just went through this, particles of a gas and the amount of energy in a gas particle, blah, 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 blah. And we've gone through the PVs, nRT, the new version of the ideal gas law. There we are. So now we've gone through this addendum page. And sometimes these show up. They're not common, but that's why we had to go through them in case they do. Okay, let's get into the more common stuff that we absolutely need to know. Not that we don't have to know the other stuff, but this we got to know. Now we're going below the line. Everything we did up to this point was above the line. Specific heat capacity, heat of fusion, heat of confusion, heat of vaporization. That's all above the line. Now we're going below the line. There's new stuff. Many of you have seen much of above the line, but very few of you have seen below that line. So let's dive in. Here we go. Work is equal to force times distance. This is a physics 1 equation. I didn't take physics 1. That's fine. You don't have to. We can go through this very quickly. Here's all it means. It's easy. Work is equal to force times distance. So if I have a calculator and I apply a force to it, and I get it to move a certain distance from here to there, I did work on this. If I move it this way, I did work on it again. I put a force on it, and I moved it a certain distance. Pretty easy. Now, work is not this. I'm pushing on the board, and I'm not moving it. No work was done. Why? Because I couldn't move the board. Okay? I'm not Superman. Superman could. You got to move something. If it ain't moving, it ain't working. Okay, so that's what work is. Force applied to something, you get it to move. Pretty easy. That's with like a calculator or a piece of paper or an apple on the table. Nice apple. It's pretty good, huh? Yeah. You're jelly. Jelly. Work, when it comes to gases, and that's what we're talking about here. Let's talk about gases. We're talking about thermal expansion of gases. As we move now, we're segueing into what's called heat engines, combustion engines, which make things move and do work. Very important in physics. Then we need to know about work done on a gas and by a gas. So this equation applies to objects. This equation applies to gases. So force is analogous to pressure in a gas. Distance is analogous to a change in volume. Think about a balloon. You got a balloon, a nice little balloon, and you take it outside in a cold January morning. What does it do? All right, bring it back inside. You're changing the volume. By changing the volume, the gases are moving a certain distance. So instead of distance, we use change in volume. With me so far? Okay. So work is equal to pressure, which we all remember is newtons per square meter, times volume, which is in cubic meters. And if we do a little analogy or a little analysis here on the units, we see that these meters cancel out with 2 of those. And you're left with a Newton meter. And a Newton meter, you know what it is, you just don't know you know, but you know, is a joule. So we're left with the unit joule. Energy units. That's energy. Remember Q? Q is measured in joules. Q is measured in joules. Work is measured in joules. Energy is measured in joules. It's all the same thing. All the same thing. Okay. All right. I look funny with this mask. I'm looking at myself. I look funny anyways. But following protocol, people. Following protocol. Okay. So that is our unit analysis. Work is a form of energy. It's a form of energy. Kinetic energy, potential energy, heat energy, work is a form of energy. They all get that unit joule. Okay, so let's get rid of this one. This is the one that we want to make sure we're front and centered on when it comes to figuring out. So if I'm looking at this bottom down here, it says system. What you say it is, environment, everything else outside the system. And that is a definition of it. It's my definition, but it works. A system is anything you want it to be, whatever you're studying. I want to study this marker. Then that's your system. Anything that's not the marker, this piece of paper, is the environment. I want to study this whole room. Okay, then the whole room is your system. Then anything outside the room, out in the hall, outside, that is the environment. Okay, simple. That's what a system is. And we're going to be talking about systems, so we have to know what it is. It's what you want to study. It's whatever you define it to be. Anything not in your definition is the environment. Okay. So what is this work done on or by a gas? And we have our new equation here. Okay, there it is. Why'd you put a positive and a negative? Because work can be positive work or it can be negative work. We have to define that. What do you mean? Okay, well, here's this. I have down here a calculator. It's on the table. I'm gonna lift it. Just dropped it. Oh, I'm exhausted. I haven't had dinner, people. I haven't had dinner. I'm hungry. I'm exhausted. Now, I had to do work on the calculator. Work was done by me on calculator. My loss, calculator's gain. There's no free lunch, people, no free lunch. Something has to pay for it. I paid for it by doing the work on the calculator. The calculator benefited. All right? There are free lunches. No, somebody's paying for it. No, that's what the definition of free is. No, I'm paying for it. My taxes are paying for it. Free to you, not free to me. You with me? Nothing in life is free. So, work done by me on calculator. I lost, it gained. I'm exhausted. The calculator's going, oh, thank you. I'm so excited now. I'm ready to go. Go home and watch some football tonight. Watch the Patriots. Oh, no, we can't. More COVID. Stupid Patriots. All right. Work positive or negative because when work is done on something, it gains energy. We give that a positive symbol. When work is done by something, it loses energy. So we give that a negative. Sometimes you'll see in some definitions in some textbooks, they do the opposite. Sometimes work done on is negative and work done by is positive. That happens. Now, if we look on our equation, here, we're going into, so there's our equation here. There's that equation that we just went over. Work is equal to power. Work is equal to pressure times change in volume. There's a negative there. There's a negative. That has to do with the definition of on and by, in which way you're using it. Okay, work is negative when work is done by something. So that's the negative there. I tell my students, just ignore the negative and think about it. Otherwise, you're going to forget what the negative sometimes can mean. So just think about it. So work is pressure times change in volume. All right? Forget the negative. Think about it. If you're doing work, you lose energy. If your work is done on you, you gain energy. Now, in this equation down here, That's the new and improved version since 2015 that AP has been using. They used to use the Q minus W. Q minus W means you have to use this here, which gets confusing to students. You can do it, it's just a different reference point. So since students get confuzzled, they said, well, let's just stick with work done on something, it gains energy, so that makes sense, right? And work done by something, you lose energy, so that makes sense. So get it a negative and use this equation here, since this will make sense. Where to go? This equation here will make sense when we use it, which we're going to be doing very shortly. I'll show you how. Okay. There's a new equation for work done on or by a gas. Okay? Now, let's talk thermodynamics. Thermo, heat, dynamics, movement. Heat movement. There are various laws of thermodynamics. In fact, the laws are listed here on this side. We're going to go through the first law. There's a zero law. The zero law is a logic law. I'll go through the zero law. The zero law is pretty straightforward. It makes sense, it's logical. Say you got 3 blocks, A, B, and C. A is in thermal equilibrium, means same temperature, as block B. Okay? B is in thermal equilibrium, same temperature as block C. Therefore, A must be in thermal equilibrium with C. It's kind of like the, yeah, makes sense, law. And that's all it is. I mean, we mention it, it is there, it's like the duh law, but we don't actually do any math with it. If you are the same as you, and you are the same as you and you are the same. Zero law, okay. First law. The first law of thermodynamics, you know. Yes, you do. You know it. I don't know it. You do. You used to know it's first law of thermodynamics. Energy cannot be, yes, created or destroyed, only changed in form. That is the statement of the first law of thermodynamics. Now, we, being physics, the apex predator of all the sciences, take that and make an equation out of it. Yes! We own, people, we own. The first law of thermodynamics, mathematically, is going to look like this. Hence, where'd it go? There it is. No, not there. Here, right there. What I was showing you a minute ago. There, that's it, right there. Okay, and you'll also notice that that wraps up the section of equations on fluids and thermo. Yeah, that's it. That mean we have a test soon? Well, not really. Not until like the end of next week we'll think about the test. But well, let's move on. We're not testing. This is the morning, and we're supposed... No, it's afternoon. Or it's the afternoon for you, anyways. It's the evening for me. I'm so confused. What is this? You know what Q is. Heat. You now know what W is. Work. Of course, this involves motion. Something's got to move. So heating something doesn't involve motion necessarily. It could, but not necessarily. What's this? Delta U. U is internal energy. Internal energy. What's that? That's the combination of all the PE and all the KE that an object has. Every object has a whole bunch of potential and kinetic energy. It could be stored energy, or it could be positional energy as potential. It could be moving energy, which is kinetic. No, you have internal energy. I hope so. You'd be dead. So you have parts moving around in you. I hope, once again, or you'd be dead. So kinetic energy. You have kinetic energy. Things move. You've got energy inside your body, even if you're not moving. I still have kinetic energy. Moving. You have potential. There's a lot of stored energy in you. We can extract a lot of energy out of you. Yes, we can. Yes, we can. Sorry, a little creepy. I'm hungry. I need to eat. I get weird, more so than usual. Okay, now, internal energy. This is change in internal energy. So if you want to change something's energy, you have two choices of how you can do it. You can heat it up or pull heat out of it. You can do work on it or have it do work. Work and energy, work and heat are your two ways to change the internal energy of a system. Now let me give you a sciencey example of that. Let's say that you have a beaker of cool water. Give me some water. I shot a man on the Mexican border. Cool water. Give me some water. Give me some water. If you can tell me who sang that song, you get an A in the next test. I will. I'll put an A in your test. I will. I'll write an A on your test. Okay. Yeah. Who's the artist? I don't know. You sound like a dying dog. That's kind of harsh. Let's say I've got this beaker of water, cool water, and it's got a hot plate. Put some buttons on it, make it look all official-like. And we crank up the heat. Little wiggly lines, universal for heat. I mean, you make a wiggly line anywhere in the world, they will know that that means heat. Wiggly line, that means heat. Ja! Russia. Wiggly line, that means heat. Ja! Germany. Sounded the same. Germany, Russia, same thing. Now, so this means heat energy going into a system. But if we want to heat up the water, we have two ways to do it, remember. We can add heat to it, or let's do some work on it. Water bottle. No Bunsen burner, no hot plate, no radiator. I can get this bad Larry to heat up. Shake, shake, shake. Shake, shake, shake. Shake your booty. Shake your booty. I've got some good lyrics to songs. I just gotta get them down before somebody steals them, you know? Oh, I'm exhausted. You try that at home. If you were here, I'd have you doing this. I'd have a volunteer. We'd pick a volunteer. Go do this for 5 minutes. I'll see what your arm's like then. Take the temperature before and after. You will get a change in temperature. I'm holding it from here, so I'm not adding any heat energy from my hand. You know, just move it around. You do that for a while. See what happens. You're doing work on the water. So we could put a stirrer in here, like a spoon, like a ladle. It's a terrible looking ladle, but don't judge me. And spin it. You're doing work on that system. Another way to increase its kinetic energy, which is directly related to temperature. So if we increase the kinetic energy, we increase the temperature. Try this at home, not for professionals only. You all should have a thermometer now. Remember your daily monitoring system form, which I fill out religiously every day. All right, try it. So let's do a problem here with the first law. Let's say that we have this beaker of water, and I add in, through heat, wiggly line, heat line, 2,000 joules of energy. And I stir it up, and add 3,000 joules of energy. What is my change in internal energy? Well, 2,000 plus work is done on the water. On the water, that's positive work. So that's positive 3,000. Anybody got a calculator? Well, wait. Did you get it? 5,000? Okay, trusting you, 5,000. 5,000 joules of energy were changed in that water. Now that would make the water temperature go up, and we could do another calculation with that if we wanted to. We could take this energy, this 5,000 joules, and put it into the heat equation, Q is equal to m delta TCP, and we can actually get a temperature change on that water. Not now. Not now. I'm hungry. I'm moving on. All right. Now, if I'm doing the stirring, that's work done by me, I lost 3,000 joules of energy. So my internal energy would have gone down. That would be a negative for me. I would have lost that energy. Okay. Next part of this video, and the part that I will wrap this up with today, are on these vocabulary words. And trust me, AP will always check to see whether or not you know these in one way or another. They will ask questions to see if you know them. Not directly, but indirectly, in multiple choice questions and maybe problem solving. So these three words are important. Let's go through them. They apply to this first law. We're going to apply these words to that first law. Word one, IsoVolumetric. IsoVolumetric. What does that mean? That means your volume doesn't change. Your volume doesn't change. So, like if you put heat into something, it doesn't expand or contract or anything? Correct. Like, give me an example. Like, that never happens. Okay, let's say you're driving to Walmart on a 90-degree July day. You go into Walmart for a half hour. You left your windows all nice and rolled up. You come back out. Okay, is that what? Yeah, you know. Open that car door. Blah, your face melts like that Raiders of the Lost Ark ending where they're just. Blah. That's what's going to happen to you. Face melting. So, but your car didn't expand now, did it? That would make it interesting if it did. I mean, parking in a parking lot in the summertime, and all the cars go like popcorn kernels, and go boom, 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 boom. That'll be more fun, maybe, or not, but that doesn't happen. So why? Because that's a rigid container. When you have a rigid container, your volume doesn't change. Isovolumetric needs a rigid container. So you can add heat into the system, but that rigid container doesn't allow that expansion. That can happen, isovolumetric. Now, on this equation, what does it do? So let's say this is your car. Heat from the sun is going into it. That's going to change the internal energy of that car. You know that when you get inside that car, your face melts. Because it wasn't that hot before. Now it's changed. Well, it changed because of this, not this. Why not any work? Because there was no change in volume. Remember, our definition of work is pressure times change in volume. And if you don't have a change in volume, rigid container, then this is going to equal 0. And so that is not why the car gets super melty face hot. So that is your first law under isovolumetric conditions. Your first law looks like that. All right? Let's go to the next word. Next word, isothermal. Isothermal, that means the same temperature. Temperature doesn't change. Like what? What are you talking about? Well, let's say that you've got something outside and it's getting heat energy. Maybe a balloon, like a balloon. I got this balloon outside and it's a cold day, but I'm outside and there's a lot of heat. It's a bright, sunny, colder day. Maybe it's like 40 degrees, I don't know. But it's bright and sunny out. A lot of radiant energy. So that energy from the sun will go into the balloon. That's Q. QQ. QQ, cry, cry. QQ into the balloon, increasing the temperature of the balloon. Now, typically, you would think, that the temperature of the inside of the balloon should go up. Not always. What if the balloon temperature is going up because the heat's going in? But what happens to a balloon when it gets warmer? It can expand, right? It can expand. So if the balloon begins to expand, get bigger, there's our volume change of the balloon. The balloon is doing work, because there's a volume change, work on the environment. The environment's being pushed against, and the balloon's like, brah, 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 pushing on the outside of the balloon. So the balloon is doing work done by the balloon on the environment. the balloon that's by the balloon, negative work. So we can have work being done, negative work, I'll put this inside the balloon. Negative work done by the balloon is a heat energy, it's an energy loss. At the same time, we're gaining energy from Q, from the sun. You can have a balance there. It's not common, but you can have it. It can happen. This is not a common situation, but it can happen. You are isothermal. That's a great example. Why didn't I think of you? Hey, why didn't I think of James and Emma J and Emma D and Will, my favorite, and Macy and Gavin and Peter and Declan and Jason and Luke and Dan and Peter. There's 2 Peters. And Isabel and Stephen and Lauren and Annabelle and Diego and Nick. I'm exhausted. And then anybody else? Oh, if you're not on my chart, you're remote. Sorry. Colby, I think you're out there in somewhere land. Okay. And anybody else ever? It's like the Academy Awards, you're trying to thank everybody. And you always forget somebody. Where was I? What the heck was I talking about? Nobody's here to remind me. This isn't good. What was I doing? I don't know. I'll look at the picture and pick it up from there. So, you are a isothermal situation. You have, what do you call that in biology? Homeostasis. If we don't maintain our 98-ish point something-ish degrees, we're in big trouble, mister, right? So we're producing heat all the time. We're releasing heat, but we're taking energy in. We eat food, we digest it, we get energy, but we're also releasing energy to the environment to maintain isothermal, maintain that equilibrium balance. There's another good one. All right, but that's biology, and biology is not a real science, so let's go to physics. So here's one where you've got heat going in, gaining energy. This goes up. But because we're gaining energy, we expand and we do work on the environment, so we lose energy due to doing work. And if the case is that these are the same, if they're equal, then we maintain isothermal. And that means no change in internal energy, stays the same. I remember doing a biochemistry, graduate level biochemistry course, and they talked about the thermal effect of a meal. When you eat food, you digest, you break down stuff, you're getting energy, but you're also increasing your energy and rate of heat loss to balance yourself out. So, isothermal means these two are the same, and your internal energy doesn't change. And remember, we started this whole thing out today, U is equal to KE. They're the same. K equal to KE. So, and PE too, but if you're changing this one, it's because you're changing this. And this is equal to your temperature change, or it's related to your temperature change. So, isothermal means no change here. These must be the same. Okay, moving on. Last one. Stick with me. Stop drooling. You're sleeping. There's no sleeping in physics. Okay. There's no crying in baseball either. And there was with the Red Sox. A lot of crying. Adiabatic. Last word, adiabatic. We all know that's a body of water between Italy and the Balkans. Oh, man, I cracked myself up. It's funny. It's on there. I wrote it. Okay. Adiabatic means no heat. No heat involved. So delta U equals Q plus W, but there's no heat. That's what the word means. That's adiabatic. Your change in internal energy is due to work only. Yeah, give me an example of that one. Yeah, what are you going to do about that one, mask guy? Okay, if anybody you ever work in like a Hannaford or I don't know, where they blow up balloons, that's a great example. The balloon blows up so quickly, you're filling up those helium balloons, that there's no time for any heat exchange. The heat exchange takes some time. That's just no time for heat exchange. All of that's due to work. That's an adiabatic example where you're blowing up a balloon so fast. When something happens so quickly, there's no time for heat to go in and out of the system. Then you have only movement, which is a work example. So adiabatic is that. Okay, we hit a half hour plus. I was interrupted, and I'm tired. It's 10 to 7. I'm going home. I'm getting food, and tomorrow morning when you're watching this, you doggone better appreciate it. Okay, Nick, do you appreciate it? Yes, you do. I know DeClan does. DeClan's a mean man. All right, so talk to you tomorrow. We'll watch this video. At the end of this video, at this point right now, when we're logging off, once you click out of this, you go and, wait a minute, tomorrow's Tuesday. Yeah, you go and ask questions if you have them, and do work, and eat food, and I'll talk to you on Thursday. Talk to you on Thursday. Thursday, we're doing a lab. Doing a lab on Thursday. Yes, we are doing a lab on Thursday. Okay, we'll see you. Bye.